Okay, everyone. So, today's content is basically going to be a history lesson about x86-64 hardware. It's just like to show you the whole how it came to be. Now, it is mostly all the architecture you use right now. It's basically a 64-bit PC you're using these days, but back then there was 32-bit, which was x86 or even like 16-bit or even worse. But like, yeah, today's content is not going to be in the exam mostly, but like you have to go through it anyway. So yeah, in 1945, John von Neumann came up with a machine, which like concept of the machine, which is called von Neumann machine, and he wrote a report on the stored program concept known as the first draft of a report on EDVAC. There was also Alan Turing, you know him from the movie Imitation Game, Conrad Zuse, Eckert, and Mauchly involved. So yeah, the basic structure proposed in the draft is known as von Neumann machine or model. So according to his model, a PC is going to have a memory, processing unit, and control unit. So we will be actually going through them one by one. So let's see. So first, the memory or memory unit. It consists of two parts. One of them is memory address register and the other one is memory data register. This holds the program instructions and data. There's our processing unit or the CPU, central processing unit. Obviously it has something called ALU, which is arithmetic logic unit, and there are some registers. Most of your variables are stored here when the PC is used, like trying to do some work with it. And then we have the control unit. Control unit has two parts. One of them is PC, which is called program counter, and IR, which is instruction register. What control unit does is decodes the current instruction, manages processing unit to carry out instruction. Program counter points to the next instruction to be fetched. So if you have a program of multiple lines, it goes through them one by one and just like sends it to the processing unit. Instruction register stores your current instruction, and we will explain that soon enough. So what happens is whenever we are at a certain line, PC takes control and then it sends the instruction address to the MAR, which is the memory address register. From there, it fetches the data and sends it to the IR. And then the control unit actually sends the signal to the processing unit. Some sort of like processing is done with your ALU and registers, and then the data is like the data address is queried to MAR, and then it gets the data, and then it finishes its work over here. So that's, and the output goes to the like some sort of like output unit or something like that. But this is basically the main idea of a von Neumann machine, and even now most of the PC can actually be explained with a von Neumann machine anyway. So yeah, Intel x86 family, it totally dominated the market. It had evolutionary designs such as like it had backward compatibility with 8086, which was introduced in 1978. It had open architecture, which basically means third-party suppliers for all sorts of external hardware and software could contribute. There were added like more features as time went by. It basically made use of CISC, which means complex instruction set computer architecture. So what it did is basically did parallel processing, and like basically do more than like be able to run more than one PC at this, like more than one program at the same time. It was useful, but at that time it wasn't that useful for Linux programs, but it was very useful for other OS and stuff. It was, hard to match the performance of RISC. So what RISC does is it runs one program at a time. So basically it dedicates all of its resource to the one program. That's why it had a very high performance. But like for CISC only focused on multiple program at the same time. So that's why the processes used distributed resources, so the performance wasn't as big. But like honestly, nobody actually could see the difference much. Like you could only see that by doing bench work or something like that. But like Intel has done just that. Like this is what they did in terms of speed, less so for low power. Okay, so a few more things to think about. So RISC, well, Celeron actually made use of RISC, and it's a fun trivia. I started off with a Celeron, and honestly, I hated my PC just because it was super slow. RISC managed to run many things at the same time. So introducing RISC by Intel was a revolutionary design, honestly. So yeah, one of the oldest PC is 8086. Like it came out on 1978. It has 29K transistors, clock rate of 5 to 10 megahertz, which is not much because now we have like what, this much clock sorry, clock speed with 8 cores. So compared to that, this is nothing, but it was pretty good. In those PC, you could run IBM PC or DOS. It had like 16-bit of processor. It had 1 megabyte of address space. Can you imagine? Like right now, you have like what, 16 gigabyte. Compared to that, this was like 1 megabyte. It used 8088, which was a modification of 8086 chip, which was used in IBM PC. It completely dominated the whole market. Yeah, this is one of the PCs. And this is how its version of Neumann von machine looked like. Then we have another addition to the x86 family, which is 80386. It came out in 1985 with even more transistors, and the clock speed also increased. So it was the first 32-bit processor. You saw that the previous one was 16-bit, right? And now it's 32-bit, and it was called as IA32 architecture. But as its name is x86, that's why it still belongs to x86 family. So it did something called flat addressing. Honestly, I don't know much about it. Capable of running Unix. So yeah, it actually managed to run Unix in it. It had 32-bit Linux GCC used no instruction introduced in later models. This one weren't available at the beginning. It was added later on. And IBM PC superseded by 386 based machines from other vendors, explosion of clone vendors. Like many people jumped into the market, like how Android is right now. So yeah, and it is its version of architecture. Then we have even more upgrade. Okay, so before Pentium 4, they had 1, 2, 3, which was kind of similar to 86, so that's why we didn't mention it. But this one was revolutionary just because it's 64-bit. Before that, most of them were 32 bits. It came out in 2004, even more transistors. Like it's literally on millions right now, and the clock speed increased drastically. And this is where it started being called 86-64, which we still call. It was based on AMD 64 architecture. So the thing is like till 32-bit, Intel created them. But like 64-bit, the first usable 64-bit was made by AMD 64. So if you ever try to install any 64-bit Linux, you will see that it's called AMD 64, and the 32 bits are called something like this. That's because of the previous machine you have just like seen a while ago, and it is the architecture of the x86-64 architecture basically. So one thing that people were afraid of is the bigger the clock rate goes, the higher the power gets. But we saw that um, it's not what happened. It was expected, but we managed to lower the power consumption. Shortly after the beginning of 21st century, an inflection point was reached. In a speech in 2001, and Intel, an Intel executive pointed out that an extrapolation of increasing power density and thus temperature of microprocessor chips would exceed that of a rocket nozzle by 2006 and of the sun's surface by 2012. That didn't happen. But the main reason that didn't happen is because we also came up with cooling systems. You already know all the cooling technologies that are out there in the market, which is pretty cool, honestly. Clearly, something had to be done, and the result is going forward, we can expect an exponential increase in the number of processors available to us and not in their individual performance. So that's why we have 8 cores now instead of 1 core, which makes sense, right? In 2008, the Core i7 came out. Right now, I think the 8th generation is going on, but this is the 4th generation. And it has even more transistors, better clock speed, and it has like 4, 6, 8 cores, and reduced clock rates actually helped out with the was compensated by the multiple cores. This is what the architecture looks like, and if you ever start working for Intel, you will have more in-depth knowledge about this. So yeah, so what we saw that like Intel attempted radical shift from IA32 to IA64. It was totally different architecture, and it executed I32 as a legacy code, like right now what we do with C, and it was very disappointing in terms of performance. So then AMD came up with a evolutionary solution, and that's why we call it AMD 64. Intel felt obligated to focus on IA64 because they have to catch the market, right? But it is hard to admit the mistake or that AMD's approach is better. Like Intel will never admit that they were wrong. I mean, if you're actually following all the tech stuff in YouTube or anything like that, you have better idea about it anyway. So yeah, in 2004, Intel announces EM64T extension to IA32. It was their attempt on making IA64. It extended the memory to 64-bit technology, and it was very similar to x86-64. All but low-end x86 processors support x64, sorry, 86-64, but lots of code still run in 32-bit mode, and that's why whenever you do some sort of like check the size of int this, and you see that it gives you 4 as an answer, and 4 basically means 32-bit. So that's why most of the codes still run on 32-bit unless you actually specify that no, I want a 64-bit. In that case, it's going to return 8. So from the von Neumann machine, what you can see that okay, in the memory, this is how your program is going to look like. It has a program object code, you know, the object file we always show you. This is where it's going to be stored at. Program data, the program has lots of data, right? Like for example, your string hello world, it's going to be stored in the program data part. And we have the OS object code. Every single program is actually OS dependent, And that's why we tell you to use your CentOS, because like the same code will not work on like other Linux environments such as like Ubuntu, just because like this part is different. It also has some OS data. And then we have the runtime stack. The runtime stack is basically the heap, and this is where all sorts of like dynamic memory allocation is stored, your normal stack is stored, and like any sort of like if you corrupt it, you cannot return to the normal program execution. Remember I showed something like stack smashed? It was because I was corrupting this part of the program. So yeah, I have already mentioned this, so that's pretty much it. Yeah. So yeah, in the von Neumann machine, the programmer visible state, PC, this one is always visible to you. It stores the address of the next instruction. It will make sense more in the next few classes, and they are called EIP in terms of like IA32, or RIP in case of IA86-64. And we have register file. This stores heavily used program data. Whenever like okay, this whole idea is from the no. Okay, so register files are basically cache. Whenever you're using one sort of like memory too much, it's actually stored in the cache, so it can keep using it again and again, so it kind of lowers the overhead. And we have like condition codes such as if else, like store status information about most recent arithmetic logic unit, used for conditional branching. It will make more sense in the assembly part, but for now you can just think of it as like if else and loop statements. That part is stored in the condition code, and that part is taken care of, well, one part of it is taken care of by the control unit. This is what the I32 integer registers look like. So it had like this register part. This is what it looks like. It has EAX, ECX, EDX, EBX, ESI, EDI. This one is used for stack mostly. These are called general purpose registers. We have some special purpose ones, which is ESP and EBP. So this one is for IA32 integer registers. And this, like EAX, can be separated in AH and AL. AH basically means A high and AL means A low. And this one is for backward compatibility with the 64-bit programs. So whenever you are trying to run a 64-bit program in your 32-bit, this whole EAX is used in this format. And 64-bit only had these 4 registers. It didn't have this. So okay, my bad. It also had those. Sorry. It had those, but the thing is, like, for these parts, these were separated. So to be able to use the whole backward compatibility, they had to make sure that EAX can still be used as a AX, CX, DX, and BX. If that didn't make sense, please let me know in the piazza. So yeah, later on we need more registers for the 86-64 architecture. So we came up with even bigger registers like RAX, and they have EX as their part. So whenever we are trying to do something like 32-bit, this part is just going to be used. This part is going to stay unused. So this is a drastical change from the 30 like x86, like from here. But as you can see, one thing is similar to this. Like, to make sure that the backward compatibility works, they made sure that EAX is like still can be used as AX, and in this case RAX is letting you to use EAX, RBX is letting you to use EBX, RCX. So the previous registers are still there, and it has more extended part, this, right? And they added more registers, R8, R9, R10, and so on. These weren't in the 32-bit. As you can see over here, they are non-existent. And these ones are called like they extended the existing registers and added 8 new ones, and they made this general purpose. In the previous slide you saw that they weren't general purpose, right? But from now on they are also considered general purpose, like this. So yeah, whenever you're writing a program, your PC cannot read this. Your PC only understands binary, so they are converted into a binary. So this is something new. Well, you were shown about this in one of the previous classes, like in the compilation and stuff. So if you do GCC and then add this and put this, it actually tells the compiler that you want a binary file. By saying this, you are telling it to make it 64, like 64-bit. And by telling it this, it basically means to do least amount of like optimization. I can be wrong, it could also mean the most amount, I have to check that. And by saying this, you are actually just telling it to use the 1999 standard of C. So this is what your like executable file looks like. You might ask, like, this is not binary. Well, this is hexadecimal, and you can just convert the hexadecimal to directly to binary. So this is what your PC actually reads instead of this. But like this is not actually readable for humans. So what people came up with is something called assembly language, which is going to be the topic for next few classes. So this is what the program looks like in assembly. We will go through them extensively in the next few classes, so don't worry about it. This is pretty fun, and this is going to be fun, and this is also going to help you learn hacking which you will be using in your binary bomb, so don't worry. So yeah, that's it for this video. If you have any questions, and if I was not able to explain anything like with ease, or like if you have any confusion, please ask me about it. And another thing I want to tell you is, like, okay, this whole slide is not going to be in the exam, so that's good news for you, right? So don't worry about it if you don't understand it, but the next few classes you actually have to pay attention. So yeah, that's it for this video. I'll see you later.